This conference will now be recorded.
Hello and good afternoon from Otaniemi, the home base of Smart Otaniemi, the innovation ecosystem on energy. My name is Sami Kazi. I'll be your webinar host today, and we'll be going through a wonderful webinar by several of my colleagues addressing fuel cell and hydrogen energy. Just to let you know, you've been all put into a mute mode. This is just to avoid any disturbances and to ensure the smooth flow of what you see on your screens and also the audio. One thing I'd like to let you know is that you will see a chat icon on your screens. Please open that up. It's like this chat bubble, and type in any questions which you may have during the webinar over there, and we will try to take them either just after the speakers or then at an appropriate moment towards the end of the webinar. So please just type your chats over there, but let's move forward. My name is Sami Kazi, once again, your webinar host. I'm a research team leader for smart cities and intelligent buildings here at VTT. And joining me today on the webinar are Professor Jero Ahola from Lappeenranta University of Technology, my colleague Ville Saarinen from VTT, and then Matti Nopunen, who's a director of technology at Elcogen. So they will be presenting to you different ideas and solutions related to their work areas. I'd like to share with you how we plan to go today. I'll spend very few minutes describing the Smart Otaniemi innovation ecosystem, what it is, the pilots and everything, and then we get into Jero's presentation on green hydrogen production. Then we get to Ville talking about an energy transition towards zero emissions. And last but not least, we get to enabling a clear sky or power generation without internal combustion by Matti later on. And at the end of the webinar, we will, of course, allow some time for questions and answers. So please do keep them coming. And as I said, you will see this chat bubble. So please type in any question you have at any time and then just push it forward. But first and foremost, let's get into our wonderful Smart Otaniemi innovation ecosystem, focusing on, of course, smart energy. One of the prime aims of Smart Otaniemi is actually to address challenges of global significance. And this includes some of the Sustainable Development Goals by the UN, including affordable and clean energy. How do we get to it? Industry innovation infrastructure to support that, sustainable cities and communities, responsible consumption production, of course, climate action, and last but definitely not least, different types of partnerships which would support these goals. The tagline for Smart Otaniemi is basically rediscovery of energy. So how do we rediscover energy? In short, how do we go from global challenges towards climate neutral energy systems and then decarbonization of society? And what we do over here is bringing in, as you see on the left-hand side, a group of excellent experts globally, and of course, primarily in Finland, to go through different types of pilots, such as end-to-end piloting, data sharing platforms, considering the city as a platform, sustainable energy infrastructure, co-creation models, etc. And then how do we learn from these and come to scalable breakthrough innovations? The focus again being scalable over here. We do pilot scale prototypes, different types of systemic solutions, explore investment opportunities, and in all of this, we try to phase out fossils in the production and consumption of energy. One of the great things about Smart Otaniemi, as compared to other innovation pilots, is that we have ongoing at the moment 11 pilots, which are delivering world-class results. And I'll show you some of these later on also. We have more than 100 partners in the network, currently a 48 million euro project portfolio, which is set to increase, a load of scientific publications, lots of visits to our showroom, and again, 2 new piloting phases are already on the way. And there has been lots of interest from abroad, and the Smart Otaniemi team has actually been visiting several countries to discuss and demonstrate how this concept could actually be extended over there also. I talked about these phases and pilots, so this is how Smart Otaniemi stands today. We look at multiple things such as local flexibility, smart mobility, building level intelligence, and then platforms and connectivity that would enable such technologies. Currently, Smart Otaniemi is about to conclude its first phase. So that has a series of pilots like the aggregator business pilot, market flexibility, smart EV charging, building level intelligence, underground thermal energy, and then of course mapped together with platforms and connectivity covering 5G and beyond, and then other enabling technologies. What also started last year was phase 2, which looks at how do we get the world's most silent refuse collection, novel integration of prosumers and hybrid energy systems, and then explore operational reliability in energy systems. 2 further phases are planned, and we hope to be starting them later on this year. They cover flexible energy systems such as virtual power plants, and then how do we couple geothermal energy with different types of district heating systems, and then of course bringing in smart energy even for water. And last but not least, in the autumn, we hope to further extend these pilots to get wind power into flexible energy systems, EV charging systems in middle-sized cities, and then different types of novel applications which would utilize building level energy systems and associated data. One of the core premises of Smart Otaniemi is it's a living lab testbed for breakthrough innovations related to smart energy, their combination, and again, everything has to be scalable. I think this is the prime premise. And Smart Otaniemi is located all across Finland, but the home base is Otaniemi, which is also a part of the Espoo Innovation Garden, hosted by the city of Espoo and of course other partners like ourselves, VTT, Aalto University, and all of the players inside this whole ecosystem. Like I mentioned earlier on, we have more than 100 plus partners. On the current slide, you just see who is involved where into the different pilots, lots of members, and of course, we are welcoming even further pilots. So if you have a pilot which you'd like to try out within the innovation ecosystem that would support scalability, please do get in touch, and we will give you the contact information of who actually to get in touch with later on in the webinar. But without further ado, this was a short intro from my side on Smart Otaniemi, and now I'd like to hand it over to Professor Jero Ahola from Lappeenranta University of Technology to guide us through green hydrogen production and alkaline water electrolysis.
Okay, thank you very much. Hopefully this works. Okay. And you are hearing me, hopefully.
Yes, perfect.
Okay,
Jero, thank you.
Because I had some problems just. Okay, I will a little bit talk next about water electrolysis technologies, and mainly those ones that are commercial, that actually, and we have researched mostly the PEM, Proton Exchange Membrane and alkaline water electrolysis. And firstly to the green hydrogen. The idea, what green hydrogen means, it means that actually we produce hydrogen from water by electrolysis, and the energy that is used there is green. I mean, green renewable based, like water, wind and sun and so on. And basically this hydrogen will be the key element how we actually convert the electricity in the form of chemical energy, and then it can be further used in different applications. Yeah, just some examples like transportation. It's especially those things that are very difficult to decarbonize, like flying and like marine application, long-term trucking, and then of course energy storages, and of course much of those this kind of chemical petrochemical applications, where you need hydrogen treatment, or then in steel making replacement of coal as a reductant and so on. But overall, the market of the hydrogen will be huge, and here are some estimates. In our research team, we collected some estimates how green hydrogen looks. So and here are, for example, you can see that we are now currently on electrolyzer market is something like last year was installed less than 100 megawatts. And what is projected that the installed base will increase by 2050 from several hundreds of gigawatts to 10 terawatts. And actually it means, in a market sense, it means that the market will from what is currently, the market will be 10,000-fold, for example, in 2050. So it means that green hydrogen will be a huge business opportunity also for Finns and all the applications that are related to green hydrogen. Okay, next to the basic electrolyzer technologies, here is the alkaline. I think that this is the first one that was invented. It was already on 19th century, and actually the idea here is that we have a membrane, and on both sides of the membrane here we have electrodes, anode and cathode, and we put electrical current there. And what happens, it's on the hydrogen side, it breaks up water molecules, and then this hydroxide ions travels through the membrane, and then you have, and with this electrical current you will produce oxygen on the anode side and hydrogen on the cathode side. And you have to, an electrolyte is not consumed, you have to just add water, and this is the most common technique used nowadays and most mature, but there is still quite much potential left anyway. The other one commercial available that we have studied is Proton Exchange Membrane PEM electrolyzer. The idea, it was 1960s when this was invented, and the biggest difference compared to alkaline is that in this case we don't have liquid electrolyte. Actually we have solid state electrolyte. It is this membrane that is able to transfer protons from the anode side to cathode side. And again, you are feeding, in this case, you are feeding hydrogen, water to the oxygen side, and hydrogen is produced on the cathode side. And one good feature of this electrolyzer type is that it's also able to make electrochemical pressurization. Because usually when you use hydrogen in different applications, you need to pressurize it, if for storing or for synthesis or for cars or whatever, where you have to have some pressure. And this is able to do also the pressurizing. But I mean that the biggest lack of, and the efficiency is about the same class with the alkaline. But the biggest problem in PEM is that are those noble metals that is using it. For example, typically on cathode side is platinum based, and then on the anode side you have iridium oxide, which is very rare element. And if we don't have any good means to mitigate it, it will limit the production of PEM electrolyzers. So, but for alkaline there is no this kind of problems. Okay, but then this is not just a electrolyzer cell or stack. You have also quite much different components around the electrolyzer systems. You need water treatment, you need transformers, power electronics, you need also treatment of the gases that you produce, or separation of electrolyte and gases. So basically, finally, we have to optimize the whole system. And there are also business opportunities related to the whole system, not just the cell, even though it's the core element. So here are some examples also, this kind of industrial size alkaline electrolyzers. The left one is Voikoski plant in Kokkola. It's this kind of 3 megawatt alkaline system. You can see that dimensions are quite big. It's pressurized 15 bars. You can see that those rods that are keeping it together. And it's this, for example, this one consumes 9,000 amps of current when it's working at the nominal load. And the left, it was so left-hand side, and the right-hand side is the 2 megawatt atmospheric alkaline electrolyzer that is in Verlet. It was the first Audi power to gas experiment or pilot plant, and we took a picture from there. And you can see a little bit different construction. You don't have the air pressure, so you don't need such a stiff structure. But sizes are about this, and if we think about future, those big electrolyzer plants will be built up this kind of components. So they will be highly modular systems anyway. So and what at LUT we have been mainly doing is this power quality, power electronics and control of electrolyzers. And what we found out is that electric power quality has significant impact on energy efficiency of water electrolysis. And here's just two pictures from our publication from power electronics, and you can see that, and those numbers, they are energy efficiency. The more red is the color, the more energy you consume. And as you can see, and left one is traditional power supply, 6-pulse thyristor-bridge, and the right one is the what we have designed, or what we have tested, this kind of modern IGBT-based system. And what you can see, there is very big difference on the specific energy consumption of depending on which kind of power electronics you are using. The electrolyzer itself is the same. So this thyristor-bridge is much more tolerant to operational point, so current, and also line-to-line voltage, how much you have to reserve voltage marginal for the degradation of cell. It practically means that. So and this is the picture what it looks like. What is this kind of current 6-pulse thyristor-bridge or thyristor-rectifier-based, and you can see that you need the current that it produces highly, they are distorted, and it also increases the power consumption of the electrolysis stacks. And addition, you are also disturbing the electrical grid side, so you need the compensation. You need additional investment for this purpose. And what we have done is this kind of ELPSU IGBT-based rectifier. We have an idea of new kind of rectifier for this kind of industrial scale multi-megawatt electrolyzers, and there are 2 patents and 1 patent application left. And the idea is that we make very smooth current for the electrolyzer. We use existing hardware. We have a little bit different. We change a little bit topology, and what we are able to do, we can decrease the power consumption of how much you need energy to make 1 kilo, for example, hydrogen. We can decrease that by 9% from this thyristor-bridge solution. We can extend the control range, and we can also get rid of compensation. So there are quite many benefits, and we'll see how this will succeed. And it is just one visualization how it would like. So it could be this kind of container-based solution that you just put in the container all the electronics and transformers and send it to the site where the hydrogen production is put. And then finally, to application of hydrogen, what we have been doing. This was with VTT in neocarbon energy project, and we actually demonstrated first in the first fuels from the air. And it was summer 2017. Now there have been several this kind of pilots globally, but this was the first one. Actually, we made Fischer-Tropsch fuels. The idea was to take CO2 directly from the air, and the electricity from solar PV. We made split the water with PEM electrolyzers, so hydrogen and oxygen, took CO2 from the CO2 direct air capture, and then made this Fischer-Tropsch product, so wax and liquid. And idea here was to disconnect, make this kind of renewable fuels that are not connected to agriculture or land use. And this idea was further extended with this food from electricity. Actually, what we did there, we replaced this chemical synthesis with a bioprocess. And this was also with VTT. And the idea was to make protein-rich biomass. And the CO2 was taken from the air also here, and we used the same hydrogen production system. The idea was so you use PEM, for example, and then also, of course, bioprocess needs some nutrients also. And so on. This is the pilot from the last summer with VTT about the first of this kind of food from the air pilot. So CO2 from the air, electricity from the solar power, and then we have their in situ electrolysis that is connected directly to the bioprocess, and then bioprocess, and those hydrogen and CO2 and nutrients are used to grow this bacterial microbial biomass, which is protein rich. And of course, and from this, Solar Food started from this research project. This was all from my side.
Thank you very much, Jero. Very, very interesting. Now, I have a couple of questions for you.
Okay.
Because, you know, there has been lots of talk about neocarbon energy and, of course, solar foods and stuff, which is in a way, you know, coming out of this research. One of the questions being, what is really the cost of energy production compared to, let's say, traditional means? And, you know, how scalable is the solution? Do you see any market disruption happening in the short, medium, or long term?
I would like to say that if you think about globally, currently for the solar PV or wind or solar PV, they are the least cost options in the world, independent of place. Of course, what is the most least cost depends. For example, in our case, it's wind and solar is the second one. And both ones are highly scalable. And then if we go, for example, to the hydrogen production side, also this equipment is also highly scalable. And also all those synthesis, they can be made highly scalable. CO2 capture can be made highly scalable. And of course, it's also needed because we have only 30 years left. In order to get zero net carbon energy system, we have 30 years left. So it has to be based on this kind of scalable systems that have learning curve. And this can be, yeah.
Yeah. Another question is, how does weather impact the solution?
Yes, I mean that, of course, weather. I mean that weather is your energy system production will be weather dependent. So it will for weather forecasts and weather will have. I mean that its impact will increase because now it's mostly impacting on the demand side, but in the future it will impact also the production side.
Yeah. And last but not least, before we move forward, one question some colleagues have asked this before from you also possibly is that, is there some way to, let's say, reduce the size of the solution and, you know, use it inside cars?
Yeah. Yes. I mean that. I mean that inside cars maybe this is the fuel cell side mostly. But,
yeah.
Yeah.
But thank you very much, Jero. And if any of you have any questions for Jero for later on, I mean, please type them into the chat box window and we'll be taking them towards the end. But now I'd like us to move forward and let me hand it to my colleague, Ville Saarinen, and he can guide you through energy transition towards zero emissions with green hydrogen. So Ville, please share your screen and you're in control.
Okay, so are you seeing me? Okay, good afternoon. I'm Ville Saarinen from VTT, from Fuel Cells and Hydrogen team. And I will give you now a short presentation of energy transition towards zero emissions with the green hydrogen. And in this presentation, I will tell you what are the hydrogen future scenarios, especially in EU level, and how the hydrogen can be scaled up. What is the role and status of hydrogen in transport technology, and why we need actually fuel cell and hydrogen cars. And then also a little bit about how to make this clean hydrogen with the electrolyzer technology, and especially with solid oxide electrolyzers, what we are investigating here at VTT and also in the Smart Otaniemi project. If we first looking about this bigger picture, like Jero was already telling,
Ville,
there
can you
are
share
many kind of...
Ville, can you please share your screen? Because you're not sharing the presentation.
Oh.
Yeah. So please hang on a moment, everybody.
Now seeing?
Yes, perfect. Thank you so much.
Okay, so if we first looking about this bigger picture, like Jero was already telling, there are many kinds of scenarios, some more like ambitious, some more like I would say business as usual. But the main message here is that hydrogen can provide up to 1/4, 24-25% of the total energy in the EU by the end of the year 2050. And if more pessimistic, then around 10%, but still the scale is from hundreds to thousands of terawatt hours. And if looking picture here on the right, especially growing sectors are transportation and heating and power for the buildings. Then how to scale up hydrogen? Important this is also with help of government or EU regulations to simulate commercial demand for clean hydrogen. But what is clean hydrogen? Like Jero was also talking about, that nowadays 95% of hydrogen is made with steam reforming of natural gas, and then that's not clean. And green hydrogen is instead made with the water electrolysis. And it's good to remember that it's only clean if the electricity is clean, made with the renewables, and of course it's needed there also support from investments and like to eliminate unnecessary regulations and so on. This is a picture what gives you maybe a little bit more better idea or visual image of this bigger picture. I have used the solid oxide technology here as an example, and a reversible solid oxide plant is here in the middle, and you can see it is connected to the gas grid and also to electricity grid, getting electricity from renewables like wind, solar, or hydro, and providing hydrogen to both industrial hubs and for mobility, for transport where hydrogen is used. It is good point to out here that hydrogen is just a way for energy storage. Hydrogen car is also electric car, so the hydrogen is just one form of electricity here. And the hydrogen technology is already here, and this will be the future. How fast everything happens depends many things like political things and regulations and so on. But there are already like tens of thousands hydrogen vehicles on the roads, thousands of hydrogen buses, and hundreds of hydrogen filling stations, and all the time coming more and more. So the message again that zero emission transport is already existing, but good to remember again that it's zero emission only if we have a zero emission electricity available made. Then the question for you is that why we actually need hydrogen cars, why we cannot just use only like a battery driven cars for all transport. And the answer is weight, energy density, and refueling or recharging time. If I explain or put this very simple, in city centers with small cars and distances less than 100 kilometers, electrical battery car is superior, like a best option. But for heavy transport and longer distances, hydrogen is the best option. If thinking, for example, like a 30 tons heavy truck and driving distance of 400-500 kilometers, if all electricity would be stored in batteries, in that case, the battery weight would be around 8 tons, and that is of course not realistic. And also hydrogen refueling is 15 times faster than charging batteries. Already now, for example, in Germany, in certain time and areas, slow charging of electric battery vehicles has become like a bottleneck, and traffic, there come like a traffic jams on recharging stations. Then from this regulation issue, I don't talk now not so much about it, but in EU level there is coming two like directives, RED II directive and Clean Vehicles directive, and here are just a few numbers, like 2021, 20% of buses need to be electric or fuel cell. 2026, 38% of transport need to be like a zero emission. And these are big numbers. And it's not so many years, and this will definitely give some challenges for municipal decision makers in towns and small communes. Then how to make this clean hydrogen? Jero was already mentioning and talking about the alkaline and PEM technology, which are already like in commercial states. There's systems available up to hundreds of megawatts and plans even for gigawatts. Solid oxide technology is still in pre-commercial states. But when in all scenarios hydrogen production will grow up to 1,000 or 10,000 times bigger in the future in following 20 years, then we need all of these technologies. They all work a little bit different way and have own benefits and drawbacks. And this solid oxide technology, what we are researching at VTT and also in Smart Otaniemi project, is interesting, especially because of its high efficiency, 80 or 90%. And if in the future producing big amounts of hydrogen, even 1% unit is a lot of money. Main point in this slide, where you can see advantages of solid oxide technology listed, like a high efficiency, fuel flexibility, and especially this reversible solid oxide technology, what is the big below, where the same system can be used for both fuel cell and electrolyzer, both for making hydrogen when electricity is, for example, cheap, and making electricity when there is a high demand or need for electricity. We here at VTT are a global leader in this solid oxide technology. Research has been done already 20 years in this field, and we do research in all levels, starting from single cells, stacks, and then up to the pilot scale fuel cell and electrolyzer systems. Then a few words of this system development, what we are doing at the VTT, what is really happening. Here you can first see like a timeline in the bottom, how the product development goes, like starting from idea, then prototype, piloting, what we do a lot at VTT, and then the actual product and the series production. And we need all the time to remember how these efficiency, operation parameters, lifetime of the system, and the price are connected together and dependent on each other. I don't go here so much in details, but here you can see how everything starts really from the modeling, like in solid oxide technology, where the operation temperature is high, 650 to 750 degrees. The system need to be very well designed. Also, for example, heat management and insulation need to be designed carefully. And here you can see this our reversible solid oxide system. There's a lot of instrumentation there, like 250 measurement signals comes from every second, and we can use the system for both, like making hydrogen, clean hydrogen, or electricity in the fuel cell mode to because the system is connected to this our household electricity network. And then the last slide, the future plans are, of course, to develop this system further on and also investigate different hydrogen storage options and compression technologies, and of course make plans for scaling up this system to industrial scale for hundreds of kilowatts. Okay, so that was my presentation. Thank you, and Matti will very likely tell more details then about this solid oxide technology.
Yeah, thank you very much, Ville. I have a couple of questions for you. First, let's start off with, the research you mentioned, which we've been doing on solid oxides for more than 20 years. Where did this whole idea actually start off with? Because, it's research for 20 years, and now we're actually seeing some pilots and activities happening. What was the sparking moment which made us actually start working on solid oxides?
Yeah, that is what we have done at VTT. Of
Yep.
course, the solid oxide like fuel cells that is already in commercial states. Like in Japan, there's like 100,000 units like installed. So that is, of course, but this is the efficiency, and then like I was listing a little bit those benefits there. That, for example, in the solid oxide fuel cell, it's this possibility to this fuel flexibility and also to get CHP, this combined heat and power production.
Yep. And you also gave some interesting numbers. I think one number, if I recall correctly, was something like we see clean hydrogen, let's say, accounting for 24% or more production of energy. Where do you see other, let's say, savings? Is it from more energy efficient buildings or vehicles, or what more can we actually do?
Yeah, it is of course in the all scale there, like starting from saving energy, and this many this is the total energy field is so like wide, like even like production or the making the materials, like especially like a steel industry, what is now in the big role, and of course those what are, for example, making a lot of carbon dioxide exhaust, then it's this kind of very wide scale where is this hydrogen is like I would say essential part in the many of those solutions.
To accelerate, let's say, the adoption of some of these solutions which you were highlighting, and also Jero, what types of policy changes or what types of new policies do you foresee are required?
It's of course very much like if we have this kind of new technology, the big picture is all the time so that this is more expensive than this what is nowadays. So it's of course a lot of what comes to the taxations and that how to push the investments. And then of course most of the time, for example, this solid oxide technology is still like that we don't have really a production lines, so automation lines to make solid oxide systems. So it's like it needs, I would say, more like this capital investments, and it's like actually many ways, like in political way, how this kind of change would be possible to do.
Yeah. And last but not least, I think in one of your concluding slides, you also talked about the need for new types of business models. Would you like to share some insights or thoughts on that?
It's actually this more this business models, they are actually also connected, for example, this kind of things that when we are like now making new products, like for example like a steel, like I mentioned, the steel industry, when they start to use the hydrogen for steel reduction, then actually this new product what they are doing, it's a new product. So it's like this I would say like environmental friendly steel. So then these are making, there's a lot of this kind of things where you can have this something what is not just replacing the something what we have nowadays. It's just like a total new way of business. And of course, like for example, what comes to the really going through towards to the hydrogen society, when all this this, for example, transportation infra and everything will change, then there's a lot of things what will be different than what we are using nowadays.
Thank you very much, Ville, and let's move forward. I'd like to now offer the floor to Matti Noponen from Elcogen to talk about power generation without internal combustion, and what he likes to say, we enable clear sky. So Matti, floor is yours.
Thank you, Sami, for your kind introduction. Hopefully the slides can be seen at the moment at your side also.
Yes,
So
they can.
my name is, okay, good. So my name is Matti Noponen, working at Elcogen as the Director of Technology. Elcogen is a company that was originally established to Estonia 2001. We have in Estonia our headquarters and our solid oxide fuel cell or solid oxide cell production line. In 2009, we opened a subsidiary to Finland, where we have actually our solid oxide stack development and manufacturing lines at the moment. Elcogen has always been a company that relies on, or our mission is to bring to the market the best available technology with the highest efficiency that can be done with these technologies. And this is why we have also invested a lot to our R&D activities. We have also been actively patenting our inventions and solutions for the markets. For the past, let's say, five years, we have been commercializing our technology, and our products at the moment have been tested in various countries and about plus 50 customers worldwide. The biggest markets for our current products are from the Asian side and then from the Europe. Nowadays we have about 30-40 people working at companies both in Estonia and Finland. The solid oxide fuel cell is a structure where we supply air to the other side of the cell and then fuel to the other side of the structure. The air, I will try to move a bit these icons. You don't see those, but a bit annoying to me. Okay, now continuing. So the air on the cathode side is reduced, and that produces oxygen ions that are then transported through the electrolyte to the fuel side, where the fuel, which is typically methane, so natural gas or biogas, this is then oxidized at the anode side to carbon dioxide and steam. And as a byproduct of this electrochemical reaction, then we produce electrons. The electrolysis mode is the reverse mode of the fuel cell. So what happens is that we actually pumping with electrons, so with current, electric current, the production of oxygen ions in the case of solid oxide fuel cell. Here we supply steam to the hydrogen side of the cell, where either steam or then carbon dioxide are then reduced to hydrogen and carbon monoxide. And then at the other electrode, we produce pure oxygen. This technology enables us to produce fuels, not only hydrogen, but also soon gases, where hydrogen and carbon monoxide are present. The advantages of the solid oxide technology is that the efficiency of this technology is not limited by Carnot efficiency, which is like in combustion technologies, because the chemical energy that is stored in the fuel is converted directly into electricity. Of course, the same applies vice versa to the electrolysis mode. The solid oxide fuel cell operates at high temperatures from 600 to 900 degrees, depending a bit on the technology. And because of the elevated temperature, we do not require to use noble metal catalyst like in polymer electrolyte fuel cells, like Jero was earlier mentioning. With the solid oxide technology, we also bring fuel flexibility with this technology. So it's this technology is not limited for a pure hydrogen operation, but we can use fuels like methane, natural gas, biogases, diesel, or any other typical fuels with certain fuel processing systems. But still, we do not produce basically any nitrogen oxides or SOx or particle emissions with this technology. And then we produce much less carbon dioxide emissions because the efficiency of this technology is much higher than based on combustion technologies. The manufacturing of a solid oxide fuel cell is fairly simple technology, but of course there's a lot of details. The cell itself, the unit cell itself, is a layered structure composed of mainly ceramic materials. On the anode side, we have actually a ceramic material, which is a combination of nickel together with yttrium stabilized zirconia. Both are common materials used by industry today. These materials are then manufactured with standard tape casting, screen printing, and sintering processes into ceramic cell structures. And then these unit cells are then assembled into a stack structure that is composed, of course, from the unit cells together with metallic flow field plates, protective coatings, and high temperature sealing solutions. At Elcogen, our products are these unit cells and stacks, and then we are collaborating with system integrators and manufacturers worldwide that either combine our unit cells into their own stacks, or then our stacks are used in systems that produce either electricity from fuels or then hydrogen or syngases from steam or carbon dioxide. Our company is producing the world-leading planar ceramic anode-supported cell structures, and these are operated at reduced operating temperature compared to our competitors. And by reducing the operating temperature brings us the added value that we can manufacture our solutions from low-cost raw materials compared to our competitors. The solid oxide technology, even though it's a single technology, it has multiple applications, starting from small combined heat and power applications, where you basically can provide electricity to single household with the fuel cell unit, together with the heat that is needed by the family. These sort of applications exist in Japan, like Ville was also saying, and these are also coming to the European markets more and more. Then another application area is larger commercial CHP applications. For example, for grid stabilization issues, that is a big talk at the moment, for example, for the Chinese markets. Then there's a lot of growing interest with the solid oxide technology also now with the transportation application, mainly because the efficiency of this technology is this high. And then one of the application, and also the reason why Elcogen is in the Smart Otaniemi project, is the electrolysis, where we produce hydrogen, and then this hydrogen can be stored, for example, for long-term energy storage applications. The advantages of our technology, Elcogen technology, is that we can give the highest efficiency available for the market. We have, for example, together with VTT, shown that with our stack technology we can exceed 70% efficiencies from fuel to electricity, and then we have shown that we can also provide the available lifetime and the cost level that these these technologies should be so that the market will take also this as the applications. Some examples of our work currently, we have, for example, been able to receive quasi-equity loan from European Investment Bank, where we are now this loan is enabling us to start our manufacturing expansion capabilities, both in terms of units of production and stack production. The plant should be opened now in a couple of years time frame. And the idea is that when the production volumes are increased, the cost of this technology will come down also quite drastically. The efficiencies, again, measured as a joint work with VTT, but also measured by other partners in our network, showing extremely high conversion efficiencies with our stack technologies exceeding 70% from natural gas. And then the same applies to the electrolysis mode, so production of hydrogen. Like Jero was showing specific energy consumption of the alkaline and PEM electrolyzers that starts typically from 4 or even going to 6. We have shown that with the solid oxide technology and Elcogen technology, we can work at about 3, which is again significantly higher efficiency that the current production techniques are bringing to the markets. The lifetime of our technology, this is one of the biggest issues always with solid oxide technology, regardless of the company. We have been running tests now about 2 years time frame and showing that the lifetime of this technology is what it should be for the real market entry also. Some case examples, we have been working together with another Finnish fuel cell company called Convion closely in a project called Lemenen, where Elcogen is producing the stacks and delivering the fuel cell stacks to Convion. Convion is then delivering 2 of their 60 kilowatt size fuel cell installations to Lempäälän Energia. Then another case example is an electrolysis where we collaborate together with ENGIE from France, where ENGIE is the system integrator, Elcogen is the provider of the electrolysis technology. This is actually a pilot case where the pilot is located in Dunkirk steel factory. The idea is that the exhaust gas from the steel factory is taken to the demo site or the pilot site, where we combine the hydrogen produced by our stacks together with this exhaust gas and producing then synthetic fuels that Volkswagen is then using in the project. Acknowledgement from our work goes to the European Union and Business Finland, and like I said, we are also receiving money for this from the Smart Otaniemi project. And last but not least, also acknowledgement to VTT for the long-term collaboration we have done in the fuel cell and electrolysis development. Okay, thank you. This was everything from my side.
Thank you very much, Matti. A very, very, let's say, impressive presentation and all the great work you're doing. I have, of course, a couple of questions for you. To start off with, what do companies need to do, or let's say building owners need to do to make this transition towards solid oxide technology?
One of the things is, of course, you have to have a connection to gas grid. So basically, typically natural gas grid or then biogas grid. which is not typical for the Finnish sites, but most of the European households are actually connected with natural gas. So it's the transition from typical gas boilers to fuel cell systems should not be that big actually for the normal European consumers. Finland has to build more gas network enabling this technology also.
Yeah. But will this, let's say, put a load on normal gas usage?
Of course. It's also a bit of transition question that fuel cells enable the real distributed power generation also, because it's high efficiency, and then when the efficiency is locally high, and we don't need to have that much transfer networks for the electricity, for example, we basically use less fuel, and also the fuel cell itself is using less fuel to produce the same amount of electricity because it's higher efficiency. So yes, of course, if everything, in principle, if the electricity consumption is not increasing, then we are actually consuming less natural gas, but of course the consumption is increasing all the time. So the natural gas consumption would also increase with this technology. It's maybe not an easy answer. It's more like a society type of questions that researchers should actually answer these sort of questions.
Exactly. And one more, I mean, you talked about Smart Otaniemi. Please tell me more, your whole experience with Smart Otaniemi, how you came in and how it has helped you in the development of your solutions and how it has impacted Elcogen in particular.
Okay, thank you. VTT was introducing the Smart Otaniemi project to Elcogen, and sort of giving the name and saying that this could be a good opportunity for Elcogen to do a pilot project also. And then we were starting to think that what is really key for the sort of household or building application, and VTT, like Ville was showing, has been investigating these reversible solutions, reversible operation mode of solid oxide technology. And this reversible mode of operation means that you can, with the same equipment, produce hydrogen, store that when you are over when the electricity production is more than your consumption, you can produce hydrogen with the technology, and then when you don't have any electricity production, for example, from the solar power, then you can again produce with this reversible solid oxide technology the electricity that the household is needing. And this is actually what we are, together with VTT, also demonstrating that with our technology, this sort of operation is possible. And the testing that VTT is doing and the piloting that VTT is doing at the moment is showing these sort of capabilities that the technology can be used in both directions without any major difficulties. And what Smart Otaniemi has brought to us is that it's basically a platform that enables us to do this sort of testing together with VTT.
Thank you, Matti. And now we'll go to the question and answer session. We'll just take a couple of questions which you may have along the way. And I'd like to start off with one we got from Heidi Tuiskula. So this goes to all of you presenters, Jero, Ville, and Matti. Do you see any challenges with regards to social acceptance with regard to the fuel cell and hydrogen technology?
May I start?
Yes, of course.
Okay, thank you very much. So I mean that the biggest thing I see that has been very difficult is that there is this opposition between battery electric vehicles, because there has been much fight for hydrogen there. And I mean that it's really unnecessary, because if you think about this whole transition, what we have been simulating at LUT, for example, globally, you need all the options, and there is no single solution to everything. Like Ville said, that batteries can be used, for example, in cars with low distance. So, but if you go to trucking, you need also some kind of chemical fuel, or if you make chips or so on. So I mean that it's unnecessary, but there has been some.
Ville, Matti, any opinions on your side?
If I can continue, it's always that when you are introducing something new to the markets, then it can be either that people are cheering that this is the best available thing that you can imagine, or then the vice versa, that like with the battery vehicle and fuel cell vehicle, that there is a competition and people are somehow not accepting the new technology without any clear reasons why this is not accepted. What is basically good about this technology is that there's so variety of applications, bigger variety of applications, that including both industrial usage and then sort of household commercial type of usage. And most likely these technologies will be introduced first to the industrial applications. And like Jero was saying, that electrolyzers are currently used in industry already. The alkaline has been there for many decades already, producing hydrogen for various applications. So from the industrial side, the resistance for the new technology might be less. Of course, then there's economical questions that what is the best available technology for the money that the companies are using, of course. Then.
We are slowly running out of time, but if I may just get, go ahead, Ville, you had something.
Yeah, I was just still this price issue, because it's every time the question comes that, oh, when this is competitive against this current technologies, but this reality is so that if we just we should just think also this environmental values there, what these are giving, and not only that, because typically this is every time more expensive than these existing technologies.
Yeah. So again, before we close, just a quick word from all three of you, starting with Jero, then Ville, and then Matti. 10 years from now, what will we be talking about?
I would say that will be the big discussion in Europe is that, do we need natural gas at all? So because when we are getting rid of fossil, the green hydrogen production is increasing. So, and we'll start filling our natural gas network with green hydrogen. And then finally the question is, do we need this molecule of methane at all?
Yeah. Ville?
Yeah, for me, I would like to definitely, after 10 years, to see in Finland more use of hydrogen and the hydrogen fueling stations and so that the hydrogen society comes also to Finland, that we are not together with Romania, this white spot in the European country, so that there would really come like investments from the Finnish companies.
Yeah. And last but not least, Matti?
We are starting at the moment the first megawatt size factory producing our technologies, and in 10 years or after 10 years, I would like to see that we are opening the second or third gigawatt size factory producing then fuel cells and electrolyzer technologies.
Very good. Thank you so much. Before we close, if you need to take a picture of any screen, this is the one you should be taking of now, because this contains the link to the website. It's the same as where you joined from today, where hopefully by tomorrow we will be sharing a recording of this webinar in addition to the slides. So you don't need to worry about that. They will all be over there. So please do pick them up. So hopefully you've taken a moment to take a picture, but otherwise, I mean, it's the same place you came on. Let me just share with you a little bit further. This is the contact information of the key people you should get in touch with. The Smart Otaniemi co-creation manager is Sanna Örni, who works at VTT, so please get in touch with her if you need information on Smart Otaniemi in general, about, let's say, wonderful magic happening from air, like fuel and food. Talk with Jero. For solid oxide, get in touch with Ville and Matti, and do come and join the Smart Otaniemi ecosystem. We call it joining the movement, and there are some links over here where you can follow up. If you have any comments or feedback on this webinar, please do let us know. And of course, I'd like to take this opportunity to thank you very much, despite challenging and testing times, for all your patience, joining us online, all the wonderful Smart Otaniemi team we have, who have helped, let's say, make this webinar a reality. And hopefully next time we will be doing certain things face-to-face. Stay safe, happy, and keep in touch with your loved ones. Thank you very much from Smart Otaniemi, and hope to see you on board soon. Thank you and goodbye.